still in section 12.2. We're talking about vector value functions, calculus. We're going to talk about integration today. It's pi.
Oh, you said pi. That's why I never knew it was pi.
All right. So on Friday we came up with a definition for differentiation of vector value functions, and because of the way we defined differentiation, we can define integration of vector valued functions. So if we have our typical vector value function, r of t equals fti plus g of t j plus h of tk, where f, g, and h are real value functions, and we're going to say that f, g, and h, they behave nicely. F, G, and H are continuous. On the interval that we're interested in, we're looking at some interval a to b. We're going to say that our integral of r of t, we just integrate component by component. So that's just going to be integral of f of t dt I plus, and we're just going to do the same thing for each component, just like we'd expect. So there's our indefinite integral, and if we want our definite integral, we're just going to put our limits in on our interval. Oops, and I forgot my dt here. There we go. So again, just component by component, we're just going to integrate each component on our interval. And one thing that we have to be careful with here is for our indefinite integral, for this top one, we're not evaluating on our limits. What do we always end up with when we take an indefinite integral? Plus c. Our constant of integration is a vector. This is an easy one to forget. Our constant of integration, when we're integrating vector valued functions, our constant of integration is a vector.
So by that you mean that it's part of the vector then, or that like it's a completely separate vector?
It's a completely separate vector. So we would say the integral, just to write it out, r of t dt equals some other vector valued function, capital R of t, plus some constant vector. And we figure out the constant vector just like we would figure out a constant of integration by having like a being given the value of the vector at a specific value of t. So we would say that RT equals some vector
I
at
see.
time
So-
0.
Okay, so you're just kind of calling CI plus CJ plus
Right.
CK as, and just pulling it all out.
Yes, and putting it into this constant vector.
Okay.
And the derivative of capital R prime, or the derivative of capital R is our small vector value function R. Just like in normal integration, so this constant vector, when we take the derivative, all those constant values, they don't affect the derivative. The derivative of a constant is 0, and we just end up with our small r. So again, our integration behaves just like integration of real valued functions. We just look at it component by component. The one important thing to remember is this constant of integration, which is a vector. What I want to do now is I'm not going to. We all are pretty good at doing integration, so I'm not going to do integration for you guys. I want to go through some examples, kind of some thought questions. So, and these are on page 847. We're looking at 83 through 86, but you don't have to look in your book. We can talk about them here. So for the first one, first idea. So the question is, we have a particle. Moving on a sphere. So whatever its motion is, it's on this sphere. We want to know, and we're going to say the sphere is centered at the origin. We're going to say, for this one, we're going to say true or false. The derivative of the position vector is tangent to the sphere. And we're saying true or false? So we have two truths. And why would it be true? Okay, so Eric says the derivative of the position vector is our velocity. So our velocity vector has to be tangent to the sphere. Otherwise, what would the particle be doing? It wouldn't be on the sphere anymore. It'd be moving either away from the center or towards the center. So if the velocity vector is not tangent to the surface of the sphere, then there would be a component of the velocity towards the center or away from the center, and it would move. It would no longer be on the sphere. So this turns out to be true. All right, our second little thought question. The definite integral of a vector value function, VVF for short, is a real number. True or false?
False.
Both says false.
Like just one real number?
Just one real number.
Yes.
False. So what would it be?
It'd be vector component.
Right, it would be a vector. So this is false. But this, could I do this? Say false, it's a vector. This one's a good one. The derivative, ddt, of the magnitude of r of t equals the magnitude of the derivative of r of t. I had one false. Why would it be false? Well, this would be a scalar function that depends on time, right? They're both magnitudes, so they both come out scalars. Or are these two scalars necessarily equal? So let me give you a hint. For you physics people, think of circular motion. Motion on a circle. So motion, if your particle, whatever you're talking about, is on a circle, what is the derivative of the position vector? Velocity, or not the velocity. The derivative of the magnitude of the position vector.
The direction of velocity. I don't know. Leading us forward.
So uniform circular motion, the speed in unit. So we're thinking uniform circular motion. What's the speed in uniform circular motion? Does the speed change?
No.
The speed is constant, but the velocity is not, because the velocity does what? Changes direction, right? So this would be for uniform circular motion. This one is false. And so let's look at a quick example of this on uniform circular motion. So let's say that R of t is, how could I write a vector value function for a uniform circular motion? Okay, sine t I hat plus cosine t j hat, and we could have k be some constant, the z value be some constant, plus k hat. So we're going in a circle. R prime of t is going to be minus, cosine ti minus sine tj. The magnitude of R prime is what? What's the magnitude of this vector? 1. The magnitude of the derivative of the magnitude of R prime. So let's see. So this is our second quantity. The magnitude of R of t. The magnitude of R of t is sine squared t plus cosine squared t plus 1. Square root, sorry, yes. And the derivative of the magnitude is going to be the derivative of this thing And what does this derivative come out to be? What's sine squared t plus cosine squared t? 1. So we get the square root of 2. And they're not equal. Well, sine squared, right, so the derivative, so we get, sorry, d dt, I forgot my derivative, d dt of square root of 2, there we go, equals 0. So these two are not equal. In uniform circular motion, the velocity changes, but the speed doesn't change. One more. Number 4. Oh, this goes back to you guys will get this one easily. D dt of r of t dot u of t equals r prime dot u prime. True or false? So Griff says false. What do we have to do when we take the derivative of a dot product? Right, we have to use a product rule. So we end up with r dot u prime plus r prime dot u. Any questions? All right, that was all I was going to say today. So homework.
For chemistry?
There you go.